Hello everybody, in this video we'll learn about regression analysis. Do you think that a positive attitude helps? To answer this question, I polled a random sample of 24 students, asking for the expected grade on the coming final exam. After the final exam, the actual grades were recorded. Is there a relationship between the expected grades and the actual grades? The collected data is plotted using the Excel scatter chart, where x the independent variable is the expected grade, and y the dependent variable is the actual grade. Glancing at the graph, you notice that as the expected grade increases, the actual grade also increases. You can imagine a line through the data, such that the points cluster about that line. It is the regression line, the line that best fits the data. In the remaining of this video we'll get into the details of the regression analysis, which examines the relationship between two variables. Do you think there is a linear relationship between the x and y values presented in Table 1? In this example, I have used fewer data in order to simplify the computations related to the concepts I'll introduce later. We want to answer the question: is there a relationship between x and the y variable? The x value is called the explanatory variable and it is the independent variable. The y value is called the response variable and it is the dependent variable. Using Excel, I generated a scatter graph. A visual inspection of the scatter graph indicates a positive, linear trend. That means that as the x value increases, the corresponding y value increases along a line with a positive slope, such that the given data clusters about that line. To get a scatter graph with Excel, go to Insert Chart Scatter. How strong is the relationship between x and y? To answer that question, we'll learn about the correlation coefficient, which measures the strength of the linear association between two numerical variables, x and y. On this page the computation of R, the correlation coefficient, is explained. Once again, the notation for the correlation coefficient is lowercase r. I'll emphasize the steps to calculate R. Calculate x bar, the sample mean for x values, and then y bar, the sample mean for y values. Calculate the standard deviation for x values, and then for the y values. I'll remind you that deviation from the mean is the difference between an x value and the sample mean, x bar. For each x value, calculate the deviation from the mean over the standard deviation of x. For each y value, calculate the deviation from the mean over the standard deviation of y. Then, multiply the pairs, add them up, and eventually divide that sum by n-1. That number is R, the correlation coefficient, which in this example is 0.9547. On this slide the correlation coefficient was calculated with StatCrunch. Let's discover the properties of the correlation coefficient. Once again, the correlation coefficient measures the strength of the linear association between two numerical variables, x and y. Independent of the values of x and y, the correlation coefficient is always a number between -1 and 1. A value of r outside this range, -1 and 1, means either a wrong computation, or a typo. If the value of r is positive, then between x and y there is a positive linear relationship. If the value of r is negative, then between x and y there is a negative linear relationship. A closer value of r to -1 or 1 means a stronger association between x and y. It can be visualized as points closer to a line. No matter how strong a linear relationship between two variables, correlation does not mean causation. If r is 0, then there is no linear relationship between x and y. As r equals 0.9547, we conclude that for the given data, there is a positive linear relationship between x and y. On the previous page we drew the following conclusion: because r equals 0.9547, a positive number close to 1, then there is a positive linear relationship between x and y. In algebra we learned that the equation of a line is y equals mx plus b, where m is the slope and b is the y-intercept. The equation of the regression line is y hat equals b1x plus b0. b1, the slope of the regression line, is given by the formula r, the correlation coefficient, multiplied by the ratio of the standard deviation of y values to the standard deviation of x values. B0. The y-intercept of the regression line is calculated using the formula, the difference between y bar and the slope calculated in the previous step multiplied by x bar. X bar is the mean of x values. Y bar is the mean of y values. In our example B1, the slope of the regression line is 1.56. B0, the y-intercept of the regression line equals to 2.61. To estimate an y value, we'll use the formula 1.56x plus 2.61, where x is the value we want to get an estimate for. The notation for the estimate using the regression line is y hat. The regression line is used to estimate a y value for any x value in the range that determined the regression line. In my example, the range of x values is from -4 to 5. So, you can estimate the y value corresponding to any number in that range -4 to 5. Do not extrapolate. Do not use the regression line to make predictions for x values outside the range that determined the regression line. Because 3 is in the range -4 to 5, you can use the regression line equation to estimate the y value corresponding to 3. Plug in 3 in the equation of the regression line. So, the y estimate for 3 is 7.29. Estimates based on the regression line are calculated for the given x data values. The difference between a given y value and the estimate of y, based on the regression line equation, is called error. You can see on the graph the given y values along with the y estimates, based on the regression line equation. I want to compare the regression line to another line through the data points. The equation of the regression line is y hat equals 1.56x plus 2.61. The other line has the equation y equals 1.9x plus 1.8. I randomly chose that line. The regression line can be imagined as the line connecting the points that represent the means of y values, corresponding to each value of x. I calculated the sum of the squares of errors based on the regression line. The sum of the squares of the errors based on the regression line is 11.52. Then, I calculated the sum of the squares of errors based on the line through the data points. The sum of the squares of the errors based on the other line is 19.29. You can see that the sum of the squares of the errors is less for the regression line than for the other line through the data points. The formulas of the coefficients of the regression line were derived such that among all the lines through the data values, the regression line to have the minimum value for the sum of the squares of the errors. Hence the complete name, the least squares regression line. What is the coefficient of determination? First of all, the coefficient of determination is calculated by squaring r, the correlation coefficient. Usually it is presented as a percentage. The coefficient of determination measures how much of the variation of the response variable is explained by the explanatory variable. For our example, we can say that 91.14% of the variation of y is explained by the regression line. When the trend is linear, a larger value for r squared means more accurate predictions. To do regression analysis with Excel, go to Data, select Data Analysis and then Regression. On this page you see the summary output for the data used in my previous example. Please pay attention to the following notations. Multiple r is the correlation coefficient. R square is the coefficient of determination. Intercept is B0, the y-intercept of the regression line. X variable 1 is B1, the slope of the regression line. Do you think that a positive attitude helps? To answer this question, I polled a random sample of 24 students, asking for the expected grade on the coming final exam. After the final exam, the actual grades were recorded. Is there a relationship between the expected grades and the actual grades? A visual inspection of the scatter graph indicates a positive linear association between the expected grades and the actual grades. As the expected grade increases, the actual grade also increases. The regression analysis was done with MS Excel regression analysis tool. In the summary output table, you read multiple r, which is the correlation coefficient. Multiple r or the correlation coefficient is equal to 0.444. The next item in the summary output table is R-squared, which is the coefficient of determination. The R-squared value is 20%, which means that 20% of the variation of the actual grades is explained by the expected grades. From the summary output you can also read the coefficients of the regression line. The slope of the regression line is 0.79, and the y-intercept is 15.69. The regression line is the line that best fits the data. It is the line for which the sum of the squares of the errors is at a minimum. From Excel regression analysis, we can put together the equation of the regression line, which is y hat equals 0.79x plus 15.69. Using the regression line equation, you can make predictions for the actual grade for any value within the data range, from 66% to 99%. Do not use the least squares regression line to make predictions for x values that are outside the range of the data. A prediction for the actual grade based on an expected grade of 60 may not be reliable, because 60 is outside the range of the data. If the expected grade is 68%, the prediction for the actual grade is approximately 70%.